Varvara Kouznetsova from Eindhoven University of Technology in the Netherlands. Title of my talk is Transient computational homogenization for locally resonant acoustic metamaterials. And this work is in collaboration with two postdocs, Kim Kam and Anastasia Krushinska, and with Mark Hirsch. Okay, I guess I don't need to talk much about metamaterials in this audience. I guess it's more or less known to this audience. I only would like to bring in a picture the particular type of metamaterials we are working on here, which are the locally resonant acoustic metamaterials. It's important we are looking here at the locally resonant metamaterials, which the working principle of which is based on the local resonance rather than on a lattice Bragg effect. So that's what makes these materials principally different from the by now well-known phononic crystals, for example. And this material was presented around year 2000 by Leo, which was made out of lead spheres covered in a rubber coating and embedded in the epoxy matrix. And then what they have measured, the existence of the frequency band gaps. The interesting thing here was that those, at least the lowest band gap was corresponding to the frequency which can be recalculated back to the order of 300, approximately 300 times the lattice spacing. So this makes these materials particularly interesting for attenuation of the long wave or low frequency or long wave, long wave lengths. And another interesting point about this material, since their principle is based on a local resonance, they not necessarily have to be perfectly periodic. So even if the periodicity is lost, their effect is still there. Okay, just to maybe give you an idea how this works. This is a simple illustration. So if you have here a rod made of this material, excited by a pulse. This is the wave propagating through this material, which attenuates pretty quickly. And this actually what's going on in the microstructure that leads to this attenuation. So the red color here corresponds, the red and blue color corresponds to the positive and negative velocity. So you can clearly see here that at a certain moment, the wave in a epoxy and in the particle are out of phase, and that local resonance effect attenuates the wave. And then by the time the wave comes to the other end of the rod, there is actually not much to be attenuated anymore. Okay, so that's the material we are looking at. In the last, let's say, 15 years, there have been quite some work on the analysis of these materials, mostly in the physics community, but also quite some work in the mechanics community. Claude gave us an excellent overview of this work yesterday. However, both, well, actually, almost all methods used for this analysis have to assume infinite structures, or they basically consider material without considering the effects of the finite sizes and corresponding boundary conditions. While you always can ask yourself question, what will happen with this local resonance effect if it starts interfering with the boundaries? Usually linear elastic behavior of the materials have to be assumed. Some of the methods have to assume the periodic arrangements and or only simple geometry, such as only spherical inclusions. And often they only can consider particular types of harmonic loadings, usually at beforehand selected frequency. However, if you want to bring these materials further to real engineering practice, one probably needs to consider other cases. So what about the finite structures? How do we consider what happens when the waves reflecting from the boundary start to interfere with this local resonance effect? What about complex general loading, nonlinear material behavior, and non-periodic arrangements? So then the questions that we ask ourselves, cannot we try to see if we can apply the ideas behind the computational homogenization, also known as FE square in the literature? Cannot we try to apply these ideas to analysis of these materials? The answer is yes, so that's what we have actually done, and that's what I would like to share with you today, our ideas on this. Okay, so before we can go into computational homogenization, we first need to carefully consider, or I would say actually reconsider, the main underlying principle behind, in fact, all homogenization methods, which is the principle of separation of scales. So usually, classically, in all homogenization methods, the so-called full separation of scale principle has to hold in order for the whole machinery to work. And what that principle says, so first of all, if you have several micro-constituents of particular characteristic sizes L, all of them have to be much smaller than the characteristic size of the macroscale, and that can be either the macroscopic size or the characteristic wavelength passing through the macroscopic size. Actually, in fact, here I also should add that the size of a statistically representative volume element also has to be much smaller than the macroscopic characteristic size, but this is sort of not of a relevance discussion for this work, so that's why I omit that part. And on top of that, so-called long wave approximation has to hold. And that says that the wavelengths traveling through each of these microstructural constituents, so the representative wavelengths of the problem of the interest, have to be much larger than their size. So if this holds, then one can assume that the microstructure or the representative volume element of that microstructure is in a quasi-state condition, and then all classical homogenization constants apply, the whole machinery works, and among other results one can show that the effective mass density is nothing else than the simple averaging of the masses of constituents, and then also momentum, among other results, is simply computed as the average density times the average macroscopic velocity. Now if you look at these local resonance materials, and so then among other things, among other homogenization techniques, also computational homogenization technique works, been applied by many people. I don't even put references here, it would be too much. Quasi-static case has been done enormously amount of time, also been done for the dynamic cases. But note here importantly that even if this is being applied to the dynamic case, so on the macroscopic scale the balance of linear momentum is being solved, the microstructure is assumed to be in equilibrium, so in a steady state condition, and then the whole computational homogenization works, where the microstructural computation then merely serves as a constitutive box, so giving the stress-strain relation to be entered in the linear momentum, and the momentum expression is in fact the trivial statement then. Now if you look at the local resonant metamaterials, then there is one principal difference. So the usual, let's say, geometrical separation of scales still holds normally, so that's not a problem. But now we have to look carefully what happens with the wavelengths of the waves going through the microstructural constituents. So the matrix in these materials still has the wavelength which is much larger than its size, where for the matrix size I take, let's say, the free space between, let's say, particles as the characteristic size of the matrix. But importantly, the heterogeneities in these materials, when they get into that local resonance, the wavelengths of that motion, in fact, are of the order of their size. So then this condition holds, and this basically what breaks the classical long wave scale separation assumption, and that's why the classical homogenization methods would not apply here. And among other results, the classical mass is not simple averaging, and the momentum is also not the simple expression as this one. Okay, so what we then need to do? So that's, again, at the macro scale we want to solve the balance of linear momentum. But now at each point and each time instance, for a given velocity and deformation, we want to know as a response the stress, but also the momentum, since the momentum is now not a simple trivial expression, so it has to be somehow computed from the microstructure. So we need to build up a microscopic problem, and we need to consider several steps. So how do we go from the macroscopic scale with these kinematic quantities onto the microscale? How do we link the scales kinematically? How do we formulate our microscopic boundary problem in such a way that it's linked to the macroscopic problem? And how do we at the end extract the dynamic or kinetic response of the microstructure in terms of the momentum and the stress? Okay, so let's start on the macrostructure. We have the macroscopic motion described by the velocity and the deformation. We saw in the macroscopic balance where we need the momentum and the stress as the constitutive quantities that should come from the microscale. And the question, how do we establish this relation? So to do so, I will now first consider limiting case, which is the steady state microstructure, just to understand what's going on there. And from that, we will see how that will be extended to the transient case within the separation, the relaxed separation of scales hypothesis that I just presented. Okay, steady state microstructure, quite simple here. So here we have solving the equilibrium. We assume that we know the constitutive behavior of each phase. In a simple case, just assume here a linear elastic Hooke's law for each case. And now, if we consider the displacement field within this microstructure, where the SS symbol means here that I am considering here the steady state case. I have here the macroscopic part, so this is the macrohomogeneous part, which is fully defined if I know the macroscopic displacement or velocity and the macroscopic deformation. Plus, basically, everything within the microstructural response that doesn't fit on this macrohomogeneous response, which I will put in so-called microfluctuation field. Okay, then I write the scale transition relations, which are typically the requirement that the volume average of the microscopic deformation should give me the macroscopic deformation, from where, after very simple Mathematica, I can conclude that if I require this microfluctuation field to be periodic, I can ensure that this condition is satisfied. Now, in addition of that, I will now add one more condition, which is usually not needed in the quasi-static computational homogenization, but I will need it later on, which is I will also require that the volume average of the microscopic displacement will give me the macroscopic displacement, which leads to condition that the volume average of the microfluctuation field should vanish. And from that, this condition you basically can consider as the fixing the rigid body motion of your RVE. In usual computational homogenization, this condition is not added, and the rigid body motion just fixed, more or less arbitrary or just to zero. Since there, the motion is not relevant, only the strains are of importance. Okay, so this gives me the boundary conditions on the representative volume elements, and with those, I can solve my equilibrium problem, which gives me the microfluctuation field. Okay, fine. Now, what do we do if we are going to the transient case? Now we are solving the balance of linear momentum on the microstructure, meaning that in addition to the stress-strain constitutive laws, we also need the definition of the momentum, but this is just the usual normal continuum, nothing special there, so it's just the standard definition of the momentum. And now we do careful consideration of the micro displacement on the RVE, where we again have these two macroscopic macrohomogeneous terms represented by macroscopic displacement and macroscopic strain. We have here this microfluctuation field, which we already know, which corresponds to the steady state of the microstructure, which is purely the result of the fact that it's heterogeneous. And on top of that, we now have an additional field that arises from the fact that the microstructure is dynamic. So there is some response in the displacement that differs from this microfluctuation field in the steady state condition, and this is exactly the field that will be needed to satisfy the balance of linear momentum. Okay, and by the way, this very important ingredient in the whole framework, because that's actually the field that will make the whole trick at the end. Okay, so I now need to solve this linear balance of momentum problem, where now only this dynamic macrofluctuation field is unknown, since this I already solved for, this I know, and these are coming from the macro scale. So I need the boundary conditions for this one. You again can choose different ones, but that's what we have chosen. So if we consider the matrix, we said that for the matrix, the full separation of scales is still valid, so the matrix can be assumed to be in a quasi-static state. So in that case, we can assume that the dynamic macrofluctuation on the matrix, so on the parts of the RVE that is on the matrix, vanishes. And on the parts of the matrix where we have inclusions, where we here assume that it's geometrically periodic, we then can assume the dynamic microfluctuation also to be periodic. Again, this is an assumption, this is a choice, but it turns out that it works. Okay, now the interesting thing, or probably the most important thing here, is what are actually the scale transition relations that now correspond to this problem. And this is actually what they are. So the first one is, again, exactly the same as in quasi-static case, nothing special here. The volume average of the microscopic deformation should give you the macroscopic deformation. Now this one, for the displacement, is somewhat trickier. And that's in fact what makes the whole trick for this local resonant metamaterial. Just for comparison, these are the scale transition relations in the quasi-static case. So this important thing here is additional term here. So now I do not require anymore that the displacement that the volume average of the microscopic displacement should give me the macroscopic displacement, but there comes a correction terms due to this dynamic microfluctuation. In fact, this dynamic microfluctuation can be seen as sort of a correlated fluctuation, as they would call it in physics or in statistical physics, while the static microfluctuation can be seen as sort of statistical fluctuation. And that's what makes the whole difference here, and that's also a sort of illustration to how to understand this scale transition relation. If you have the macroscopic motion, so that the whole unit cell sort of moves with a certain displacement um, the microstructural locally resonating particle does not necessarily move with the same displacement, but it, as a matter of fact, moves even in the opposite direction. And that's sort of a graphic illustration of this relation. Okay, now we need to go back up the scale. So to compute our constitutive quantities, usually in computational homogenization, the Hill-Mandel principle is used for that. And no difference here, except that we now need to add terms corresponding to the variation of work due to the acceleration. And again, going through the whole machinery, we can conclude that the effective linear momentum is the volume average of the microscopic momentum. And the effective Piola stress, so Francesco, it's Piola stress. By the way, just a side remark, it turns out that in homogenization at large strains, the Piola stress is much handier measure than the Cauchy stress. So all homogenization and finite strains usually written in Piola. Okay, but that was the side remark. So what's actually important here is that this is the scale transition for the stress. So we again have the classical term, which is the volume average of the microscopic stress, plus this term that is sort of, that includes the momentum, and this term is in fact the sort of the RV size. So xc is the center of the RV, and this is then position of the point with respect to the center. And this is then the adic product of these two. Also interesting to note here is that this term will also introduce the size dependence in the whole simulation, so that the result of the local frequencies will depend on the size of the microstructure, as it is of course the case in these materials. And another important note here is if the microstructural size gets small compared to the wave size, this term will get small compared to this term, and basically we sort of go into the limiting case of the quasi-static case. So another nice feature of this framework is that it basically has the quasi-static case as its limiting case for the infinitely small microstructure. Okay, so this is just a brief summary of everything what I said. Now the question is actually, does it work? It actually does. Actually, the movie I showed you in the beginning, that was in fact the result of computation using this framework. But now interesting to sort of verify, does it give the right answers? And I am here now not so much interested in really studying the behavior of these materials in terms of the effective masses and the band gaps. This has been studying already quite well. What I'm now interested in is in verifying if my approach gives the right answer by comparison to the reference solution, and the reference solution is the direct numerical simulation. So what we consider here is in fact looks like a rod, but that's actually a plate infinite in the vertical direction, so that's why it can be approximated by a sort of 1.5 dimensional problem. So we have a plate of this fixed length, and for the direct numerical simulation, which I believe gives me the reference solution, so that's sort of the answer believed to be correct, I just put a number of these RVs, so how many depends on the size I'm considering, all together, put finite elements and run the implicit transient finite element analysis. Now, for the computational homogenization on the macro scale, I have this sort of 1.5D element, so that's a one-dimensional element with 2 degrees of freedom, horizontal and vertical. And on the micro scale, I have this microstructure with the materials and properties as in that material of Liu. So I have epoxy matrix, lead inclusion, and the rubber coating. So everything time discretized with midpoint Newmark scheme, finite elements, implicit finite elements, and linear elasticity and small deformations for all material properties. And this rod is excited by an impulse of a certain frequency. What I'm now going to look at, I will first fix the size of the microstructure and apply impulses of different frequencies. So I want to see if I will have a wave attenuation at certain frequencies. And then I will fix the wave length of the macroscopic excitation and look if my model is indeed sensitive to the size of the microstructure. And for comparison, I will be plotting the velocity profile along this bar, basically along this plate. So that's sort of a busy graph, but you don't really need to figure out what all these lines mean. The most important thing here is to see that the symbols that represent the computational homogenization results for different frequencies are almost exactly on top of the continuous lines that represent the direct numerical simulations. So basically the conclusion from here is that the computational homogenization does the right job and gives you the right answer. Now this sort of maybe more interesting picture, this is the maximum velocity in this rod at a sort of arbitrarily chosen moment, which is 1 over frequency, but just an arbitrarily chosen moment without any physical meaning here, as a function of the frequency of the applied excitation. And so the black symbols here are the direct numerical simulations, and the red symbols are the multi-scale simulations, and again they are exactly on top of each other. And you see that for certain frequencies you indeed get the deep frequencies, so that's actually the local resonant bandgap frequencies. So the computational homogenization correctly reproduces those frequencies. Okay, now let's fix the frequency and see if the whole simulation is sensitive to changing the microstructural size. Why is it interesting? If you take the homogenization method, any classical homogenization method is basically insensitive to the physical size of the microstructure due to this full separation of scale assumption. So now let's see what we have here. So again, the solid lines are the direct numerical simulations and the symbol of computational homogenization. And again, this is longitudinal velocity along the bar. And clearly there is a size effect, so for different sizes of the microstructures and the same excitation frequency, the velocity profile is different, meaning that the material is indeed sensitive to the size of the microstructure. Maybe interesting thing to see here is the pink line, so that's the computational homogenization, let's say quasi-static computational homogenization, I would say the classical computational homogenization, or for that matter any classical homogenization, which assumes the steady state microstructure. That would be the answer of that simulation, which is clearly size insensitive. That's why it's only one line here. And the dots, which are not exactly on top of that, but next to it, they correspond to, let's say, a relatively small microstructural size. So the computational homogenization, the dynamic computational homogenization for the vanishing microstructural sizes basically converges to the infinitely small microstructural result with the decreasing microstructural size. Okay, so that's it. I think I am well on time. So hopefully we have some time for discussion. So just to summarize, I presented the new transient computational homogenization framework for materials with microstructural effects where by microstructural effects, in this case, I mean this local resonance effects, which goes beyond the classical long wave length limit. It uses the non-conventional scale transition relations for the displacement and velocity, so not a simple averaging. And that's, in fact, the crucial point here. That's actually what does the whole trick. And then we consider the application of this approach to the local resonant acoustic metamaterials, and we shown the excellent agreement with the direct numerical simulation, which is in this case believed to be the correct solution. And we think that there is a great potential for the application of this approach for complex microstructural geometries. So again, where geometries are finite with the possibly complex boundary conditions, nonlinear material behavior, structural response of finite structures, where the structural response itself can start interacting with their local resonances, and arbitrary complex loading. So, thank you.
I understand that you want to present quickly, maybe you will tell me later, but can you start drafting how you build the microstructure like WSS you wrote?
Which?
Numerical simulations, the whole theory.
Let me.
WSS.
Yeah. Okay, this one.
Yeah. Also for doing your numerical simulations, you need to give them in terms of the macro.
Yes. So what you basically do? Maybe let me go one slide back. Then it's maybe more clear. So what you basically do? You have this relation for the displacement. You can basically substitute this into the into this.
Yes. Okay.
Yeah.
You solve.
Yeah. Basically, you solve. So in principle, you only need to solve for this.
Okay. So it's the standard trick.
It's a so this steady state problem is a very standard computational homogenization for basically for the.
And you do the same for the dynamic. So in microtime.
Yeah. Except this one that the displacement, the macroscopic displacement, is not fixed arbitrarily, as in a classical computational homogenization, but according to this relation. That's the only difference.
Is your homogenization scheme sensitive to the choice of the center of the and also the number of unit cells we consider in one microscopic problem?
Okay, so it is sensitive to the choice of the center, but I mean in the sense of the center, not so much where that center is, either it's in the matrix material or in the particle, but it has to be really the geometrical center of the RV. But that's clear to understand, otherwise, you're doing something strange. But it is not sensitive, we have checked that, not sensitive to the unit cell size. So if you take 1 unit cell or 4 unit cells, you get the same. Again, why? Because you're working here on the local resonance. So it's only matter what's the size of the inclusion and not so much what the size of the RV. So in that sense, it's difficult to say for the homogenization for, let's say, gradient continuum or Cassirer continuum.
Just a short comment. I know some of your previous results about homogenization of civil layers, and that's the same structure like this acoustic metamaterials was used in some solar cells. They modified the surface layer by using such kind of microspheres, glass microspheres to absorb more energy for this. So I guess that maybe this can also be some homogenization techniques for this.
Yeah, would be interesting. Yeah.
Surface layers.
Yeah, if you can send me some references about that. Yeah, because we just haven't seen that, but would be interesting to try there.
Just a small remark about the words, about homogenization. I mean, you say homogenization principle doesn't apply. Indeed, it applies since you have scale separation, in fact. But the classical homogenization, you have to use homogenization with inner resonance. And my question is, in your process, what is the difference with what you get with the asymptotic approach with linear resonance? What would be the strong difference? Because I didn't have seen it.
I think there is not a principal difference there, except that this framework opens the possibility to go to the nonlinear material behavior, to complex structures, and
But in case of linear, it will be the same.
I think it will be the same, except that I think you have to beforehand assume certain harmonic loading at certain frequency. No? I'm not sure if I'm mixing your paper with some other paper.
At least you have to assume that the frequency range, the spectrum that you consider, is below the diffraction frequency. But it's not necessary to have harmonics.
No, I think there is no principal difference, except that this one opens the possibility to go into complex nonlinear nonlinear material behavior and complex geometries and loadings. Okay. That's
Last question.
In your simulation, did you see these inclusions rotate?
No. And we actually have shown by other analysis that Anastasia actually showed that these rotational modes, which are in principle there, they are not able to produce the resonance.
Why?
I can show you later, but these are not resonant because you're not able to excite those modes in these materials. You can show that this mode is there, but it will not be excited for the local resonance case. These are the torsional modes. They are there, but they are not giving local resonance.
It's strange. Okay.
Excellent. Thank you.